Thank you. Well, thank you. It's a pleasure to be here, and I want to thank the organizers for inviting me. It was a real honor to be here, and I've enjoyed it. And I thought what I would do today in my 15 or 20 minutes or so is talk to you about what I've learned from participating, starting, judging these competitions for the last 20 years or so. And maybe that would be something that would help you. There's some common features that I've seen. This is just a plot of the participants in the RoboSub competition, which started back in '97 there in Panama City on the lower left. And actually, I'm one of the guys kneeling down there about 20 years ago. I guess probably look a little younger then. But and my only point here is that there have been a lot of students competing in these competitions, and I started this one, but I've been a judge of this for 20 years, and I've judged in the Eurathlon, European one, the May, RoboSub, RoboVote. And what I would hope to spend my little bit of time today doing is sharing what I've learned, because I see some common things that I think would be good to think about. Just think about and share. But it's certainly a huge community. The people who participated in the early ones here, a lot of you people weren't even born yet. And they're mid-career people now. So, you know, how do these competitions influence? Where are you going to be 10 years from now? Good question, right? And how did what you learned here affect that and your success? And I think it will, maybe not in the way you think, but definitely it will. So one of the things, I drew this little taxonomy chart because 20 years ago, there weren't that many robotic competitions. Nobody talked about robotic competitions 20 years ago that I know of, and autonomous vehicles for that matter. Autonomy, big buzzword today, hardly ever mentioned. And so people get confused now when we talk about the underwater autonomy student competition. I find they get confused. So I drew this little map so they wouldn't, because you know there are at least 4 different categories of competitions, what I would call under the general phylum of robotic competitions. There's this one, which I consider to be an educational goal, learning competition. But then there are these grand challenges, the X Prize, the et cetera, the DARPA Grand Challenge. And then there are games, soccer, whatever you want to call it. And then there's of course, the combat ones, RoboCombat, so. And these are all robotic competitions of various sorts with different goals. And, in the combat one, the goal is to kill the other robot, one way or the other. Certainly not what we're doing here. But sometimes when people only see, autonomous underwater vehicle competition label, they're not clear about this stuff. They think, oh, this is some kind of combat thing. This is a grand challenge, with a $10 million prize. It's not. But under the learning exercise, then there's MATE, like the human control, which is an ROV competition. And then there's the autonomous ones, which is this one. And then there's a number of types of platform types, like Robot X, for example. Everybody has the same platform. It's a category. This one is more on the free form end, although we do constrained size and weight. So that's why I call it sort of a constrained thing. So that's another choice you have, and there's trade-offs among those. It's interesting. I mean, there's the Formula One, on this end, and then there's, free form things. And there's trade-offs. But anyway, that's the space we're in. So what's it all about? In my simple view of the world here, it's about 3 things, really. System engineering, underwater, machines, and autonomy. And I'm going to just talk a very little bit about each of those. The lessons I've learned from my participation in competitions, and then just talk a little bit about where we're going from here. And I hope that leads into the panel discussions. And system engineering was really the goal, the learning, what we were trying to foster learning about from the beginning of this, because it's not something you normally get a course in school. If you're an engineering student, you get your core curriculum in whatever field you're in, but you are in electrical, mechanical, computer. The first thing you discover when you try to make one of these vehicles is you need all of those people. You can't put one of these, even the simplest one, together without a software guy, a mechanical guy, electrical guy, and they have to learn how to work together in designing a vehicle. Well, that's, again, not a course you normally get in school. So there's a lot to be learned there, not just about the technical aspects of that, but about the team interaction and all the other, financing the whole operation. So these are important lessons. So I just want to very briefly, cover just these things, and maybe you'll get something out of it. The first thing you really want to ask in any system design is what do you want the system to do? I mean, this is a very important question. Before you go charging off and bending metal and making hardware and writing code, and for fundamental autonomy, my view of the world is these are the behaviors that all autonomous actions actually are composed of. I mean, you need to navigate around the world somehow. You know where you are. You need to perceive things. You need to either deploy or retrieve objects. You certainly need to survive, which is not too hard in the swimming pool out here, but when you go into the real ocean, it's a little bit. You need to be able to plan and communicate. So, and various tasks are built up of these combinations in various degrees of these fundamental behaviors. So this is always an exercise in the future, 10 years from now, if you're designing a system for something, first thing you want to ask is, what do I want to design it to do? It's very important. So I don't want to go through this, but we've started categorizing tasks. The upper left one, for example, which I'm sure you hardly read, is one that's been in every competition, autonomous student, going through the gate. And we're trying to do this, and I'll come back to this at the end, because we're also, we meaning organizers of the competitions, are looking to see what common features should there be amongst these competitions, now that they're all growing in different places. Are they just going to be totally independent? So these are just typical tasks that you would combine the fundamental behaviors. So here are my persistent observations over 25 years, or whatever, okay? And this is it. This is both one slide. I got them all here, so we can talk about them, but this is it. Okay, first of all, as Harry just mentioned, all of these competitions, in my experience, have the same spirit. It's hard to quantify this, but as soon as you walk out there, you can feel it. And they're all the same. This collaborative, competitive interaction, kind of a sweet spot. They're energizing events. I always found them to be very, and I was always came away from these things with, hope for the future. There's really some great students out there, and they're really, talented, and they're working together, and now that it's gotten so international, it's even more encouraging to see the diversity of all these. I mean, RoboSub, when we started, there was 4 teams, like I showed you there, and they were from the U.S. Last year, 6 out of the 8 finalists were not from the U.S. So that shows you the evolution over 20 years of globalization in the world. So it's just amazing to watch the interaction and the energy of it all. So this is a common. These 5 things there, whatever they are what I consider, what I've seen as common features of all of these competitions, and that's certainly one very important one. The second one is that sensing and intervention tasks tend to be engineered at the expense of basic vehicle navigation and control. I've seen this consistently. Engineers love to look at the hardest task and work and engineer it all, and they never get through the gate. They can't steer a straight line. That's why I say, on that first thing, when you're designing a system, figure out what you want it to do and what the priorities are, and then, direct your energies toward those priorities. And energies and time for students are very finite resources. I'm going to come back to that. And that's one of the problems. And the second one there, or third one, is that the engineering tasks tend to be decoupled from the strategic game plan. It's basically what I've been saying. It's a game. This is a competition. The idea is to score more points than the other teams. So, does the engineering, what's your strategy for winning? If you look at the history, 20 years for RoboSub, you'll find out that you did not have to complete all the tasks to win almost. There was only 1 or 2 years when the team completed all the tasks. So if you're going to design a vehicle to complete all the tasks, okay, that's good luck. I'll come back to that, but it will be too complex. I'll tell you right now, and you don't need that to win. So, what is your strategy, and how is the engineering coupled to that? As I tell my colleagues in the professional AUV world, which I was in for a long time, and some of my colleagues here are still in, and I still tell the Navy people this too, we know how to design underwater vehicles. There's a long history and a lot of talented engineers. Tell me what you want to do. I mean, there's no generic, you just, okay, we'll design it, but you got to tell me what you want to do. So take some time at the beginning and have a strategic plan about how you're going to compete and how the engineering is coupled with that. And that leads into the second to last point, which is there's this connection between complexity and reliability is not appreciated at all. We'll just keep adding tasks and just put this actuator on, put this, this thing on, that thing on. You can do that, and you can make it reliable. You can make it work if you have enough time to test it. And I can tell you, for a complex machine, and these are relatively complex, as simple as looking as these things are, they are complex. You don't have enough time. Professional people barely have enough time, but full-time students. So that is really that connection between complexity. So you want to try to figure out where's the sweet spot in simplifying the system, and how can we make it reliable. And of course, that's very much related to the last bullet there. I always used to say this at the banquet thing. One lesson I'm sure you've all learned already: it's hard to make things work underwater. Okay. That's one other thing that distinguishes this competition from all the other land ones. People run around, airplane, drones. Water is insidious. It'll get you if you're not careful. So, and especially salt water. This is but so it's just something I'm sure you've learned already. So here's an example. I just wanted to give you a feeling for this business about reliability versus complexity. And I take this example from an unmanned aircraft, which is actually about the same as complexity as one of these AUVs, in my opinion. It has all the same functionalities. It flies in the air versus underwater. But this is the Predator. And the reason I took this example is there's a lot of data for this. There's a lot of data. And you'll see here.